If you are wanting to learn how to design your own custom printed circuit board, then in this video, I'm going to show you exactly how to do that. Hi, I'm John Teal. I'm a former microchip design engineer and an entrepreneur that brought my own hardware product to market. And now I help other entrepreneurs develop and bring to market their own new electronic products. The board that we're going to design is a microcontroller board based on an STM32 microcontroller. The PCB design software that I'll be using is called Trace, but I'm going to be focusing purely on the fundamentals of PCB layout design and not on the specifics of the software. So it doesn't really matter what software you use, and you can use any PCB design software that you wish to follow along with this tutorial. I'm going to be focusing entirely on the PCB layout process, and I will not be covering the process of designing the schematic diagram. Okay, so here's the schematic circuit diagram that we're going to be designing the PCB for. We have a USB connector here, which is purely used to power the board. The USB connector can provide a 5-volt DC supply. That feeds into a linear regulator on the board, and then that linear regulator is going to output a 1.8-volt supply rail, which is the supply that's used to power everything else on the board. Next, we have the accelerometer, which is a sensor that we're using for this example board that can measure acceleration. And then we have the programming connector itself. This is what we'll use to program the microcontroller. Although in this course, I'm not going to be getting into the programming side. We're just focusing purely on the PCB layout. And then here we have the STM32 microcontroller itself. I'm going to be referring to this schematic throughout this video as I design the printed circuit board, but I'm referring to a printed out version of the schematic that I'm using. So it's going to be really helpful if you have a copy of this schematic that you can reference while you're going through this tutorial. So below is the timestamp right now on the schematic that you can see. So you can either jump back to this point in the video to look at the schematic, or if you just take a look in the description below, I've got a link so you can download a PDF version of the schematic so you can just print that out and more easily follow along. Okay, let's get started with the PCB layout. Okay, so the first step is we're going to have to place the components. So we can, we have a lot of flexibility on how we're going to place these components. And what I'm going to do is I'm going to start with, this is the USB connector, and it has to be at the edge of the board. And you can even see here, it says board edge. It's kind of hidden a little bit by the line, but this gray line that you see, that's supposed to align with the board edge. So I'm going to just select it and then do an R to rotate it around, because I want it on, I'm going to put it up on the top left side of the board. Okay, so that's where our input power is going to come from. So next I'm going to take the LDO and I'm going to move it over near where the input power is coming from. So I'm going to rotate it. This green dot here signifies pin 1, but we can rotate these parts as needed to simplify some of the routing if necessary. Okay, so I'm going to just move this over pretty close to the USB where the power is going to come in. So if you're looking at the schematic, the input voltage, we have the 5 volts coming from the USB, and that's going to go right into the LDO input, which is pin 1. Okay, so U3 is the accelerometer, so I'm going to rotate that around also so that it's up here, and pin 1 is in the left corner. And again, that's just the starting point. As we start to route, we may find that it's better to have this rotated to a different orientation. And then U1, this big guy here, this is the microcontroller. Same thing here, I'm just going to rotate it around. So pin 1's in the left. This big guy here is our real-time crystal, the 32.768 kilohertz. This is only necessary if you want to measure real-time with the microcontroller. And this is our programming connector, so I'm going to just kind of start with it over here. And yeah, so there we go. We kind of have our main components placed. We still have all these capacitors. Let me just kind of move these down here so we have them all together. Okay, so now we can start routing. You can really start anywhere. There's no particular order. So the first thing is I'm going to route from, this is pin 1, or the B bus pin on the USB. So this is going to be at 5 volts. And I'm just going to connect that up to pin 1 of the linear regulator. And let's look at one thing here. You can see I'm using a trace width of 6 mils. 6 mils is what I'm going to use in this case. That's a pretty standard minimum trace width. You can go down to 5 mils. Some processes will go down to 4 or lower, but then you're getting more expensive processes that have smaller feature sizes. So I wouldn't typically go below 6 unless you need to. And then as far as current, everything in this design is just a few milliamps. There's not really anything that's high current, even though this linear regulator can handle up to 180 milliamps. We're not going to use anywhere near that amount of power. But even if we were, a 6 mil trace is still sufficient for 180 milliamps. In fact, let's look here at, this is just a trace width, a PCB trace width calculator that I like to use. If you just Google PCB trace width calculator, all kinds will come up, but this is one that I like to use on advanced circuits. So basically what you're going to enter here is, right now I've just got this set to a 1/2 amp just to show you. So that's the current that I'm looking to send through a trace, the thickness here of the copper, and I've got this set in ounces per square feet, which is the unit that the PCB manufacturer will specify their copper. This can be also converted into an actual thickness of the copper. But we're going to leave it at 1 ounce per square foot, which is pretty typical and kind of on the lower end. You can go higher if you have higher current. You can also go lower, down to usually about 0.5 ounces per square foot. But I'm just doing 1. It's a nice easy number. And you can see down here in the green, it gives you basically the answers for what you've entered. Oh, I want to also quickly, I'm specifying the temperature rise, because that's what happens if you pump too much current through a trace. It heats up enough, it melts, and it becomes an open. So we're just using allowable temperature rise of 10 degrees C. And what you can see down here, it gives you different answers for internal layers versus external layers. External layers can carry more current just because there's better airflow, because they're the exposed layers, the top and the bottom side. So they get airflow, they don't heat up as much. Internal layers don't get that airflow, so they can't carry as much current. So to get a 1/2 amp of current on an external layer, you just need a 4.5 mil wide trace, whereas an internal one requires 11.8. We're only doing a 2-sided board in this case, so all of our layers, our 2 layers, are going to be external layers. And what you can see here is that we're using 6 mil, so we can actually, let's just see what if we bump this up. Yeah, we can go up to about 600 milliamps or 0.6 amps with a 5.85 mil wide trace. So we're going to be totally fine. We're only using a few milliamps. I just wanted to show you how to use this tool for if you do have high current applications. Next, let's go ahead and place the capacitor that's on the input, and that is C6. You can see it highlight over here, so I know this is C6. I'm going to rotate it, and I'm going to put it up like this. So if I put it down here, it can block these other pins and make it a little bit problematic to get to. And then we can also route the, I can go ahead and you can see this pin here also highlights when you select that node. This was the enable pin for the regulator, and we're going to just tie it high. And it's not at all critical. It's just basically a digital input, so you can just tie that high. Then we have our output. So let me just go ahead and just draw an output trace. And I'm now going to see what capacitors. And for this, I'm going to refer to our schematic. The problem here is that you can see it's highlighting just about everything, because this is our main supply rail. So lots of things go to it. So it's not immediately telling me which capacitors are supposed to be placed near the output pin on U2, or which single capacitor. So you have to refer to the schematic for that. And it is C1 is what we're going to do here. So here's C1, and I'm just going to place it like here, like that. Okay, so we have our input power, we have the input capacitor, we have the output, we have our output power, and we have this is going to be ground. Well, I'm not going to connect up any grounds right now. That's the last step that we'll do because we'll be using copper pores, which will fill in all the empty space with layers, and that will be grounded. So that will take care of connecting up a lot of these grounds. And then we'll just have to go back and make sure that any grounds that were missed that the copper pore couldn't reach, then we'll manually connect those up. Next, we have the bypass capacitor or the noise reduction capacitor for the linear regulator, which is C2. I'm going to rotate that, and we'll just put that right here, like that. Okay. Now we need to connect up the power for the accelerometer. Let's see. This is going to see here the power, this pin here is just the select that tells it to use I2C or SPI. So it doesn't really matter. We can route that anyways. But these two lines here, these are the main input supplies. So let's just rotate this around so that those are better placed. Yeah, like this, okay? Then we can just essentially move this up, and I'm just gonna, let me zoom in here so I can see what I'm doing. There, so you can see now we have a trace. This is coming out of the linear regulator and going into the input pin, the VDD pin for the accelerometer. And you will recall the accelerometer had two input capacitors. If you look at the schematic, it has on VDD, it's got C11 and C12. So I'm gonna just, C12, and oh, C11 hiding over here. And for these, I'm going to, let's move this out. Oops, let me actually connect that up. Okay. Now the trace will expand as I move that part around. And we could put these here, but I don't want to block these pins here. So I think I'm gonna rotate these, around. It's closer together, like both of those. Yeah, like that. Then we have our VDD-IO, and that has its own capacitor, and that was C13, which is just 100 nanofarads. So C13. Rotate it around. Put that right here. So that's going to connect to this pin right. Let me deselect. Like that. Okay, so now we have all the input decoupling capacitors for the accelerometer. Next, let's see what we have on the, let me refer back to the schematic. You'll be going back and forth between the schematic and the printed circuit board quite a bit. Now we just have a few of the miscellaneous well, we have two pins that we want to connect up on the accelerometer. The first was the chip select pin, which we want to, is this pin here, and it needs to tie to the input supply. But ideally, okay, yeah, this is a chip select. So what I'm going to do is I'm going to just route straight across here like that underneath the part. So you can definitely route underneath parts. You have to be careful. If this was like an oscillator, then I may not want to route digital lines under it, but you can generally route underneath parts, assuming they don't have a power pad. Some parts will have a huge pad under here that kind of blocks everything, and that's essentially just a ground pad that helps with power dissipation, so that the heat dissipation, so the heat goes through that power pad and gets dissipated into the ground plane. But for this part, we can just short those two together like that. And then we have the only thing left, we have the ground pins. We'll do that with the glass. We'll do that with the ground plane. We have this pin here. This is the I2C. We'll do the I2C, the connections later. I just wanted to get basically all the power in some of the localized connections, like connecting up the enable pin or the chip select pin. Okay, so now we've got the linear regulator, the accelerometer. Let's go down and do some work on the microcontroller. Once again, let's start with the input supplies. It is on pins 5. This is VDDA, and then over here on pin 16 is VDD. So we have two decoupling capacitors for each of those. Okay, let me refer to the schematic. We have on VDD is C4 and C5. So VDD is on this side, 4 and 5. So just kind of copy down there. And then I'm just going to route from that pin just straight through both of those capacitors. So they're both connected. We may have to fiddle with these a little bit later. One other thing I want to point out is you can see the green, those are the reference designators, so they just show the part number. And you can see in this case, I've got that where it's overlapping pads, and you don't want that because basically those won't show up. We'll fix that at the end once I have everything placed, then we can kind of go back and make sure that all the reference designators are not overlaying any copper. We have those two, and now we need the 2 input capacitors for the VDDA, and those are 7 and 8. And we'll do the same over here. We'll just put those right here. Zoom in and connect those up. Okay, so now we have our input capacitor, we have our input supply done for the microcontroller. Next, we have the reset capacitor, which is C3, and that goes to pin 4, which is here. And this one we're going to need is capacitor C3. You can see placing this is a little tight because I want these are important, a lot more important than this cap. This cap can be placed anywhere. These are decoupling capacitors and need to be as close as possible to the pin they're protecting. So what I'm going to do is I'm going to just place this down here bottom, and then just route underneath the chip there. Okay, so now we have the C3. That's the reset capacitor. This is ground. Like I said, we'll get to that when we'll do the grounds last. Okay, let's go ahead and do the crystal now. So the crystal is going to connect to pins 2 and 3 over here. And even though this is a low frequency crystal, just above 32 kilohertz, it's not nearly as critical if it was megahertz or tens of megahertz or hundreds of megahertz, but it's still, I don't want the crystal over here and then routing it all around. That's not a good practice. So I want this to be as close as possible. I'm going to just place this over here. Problem is the programming connector is a little bit in the way. And you can also see here's our 2 programming lines. They're on the other side of the microcontroller. So what I'm going to do is I'm going to swap. I'm going to move the programming connector over here. Let me get these capacitors out of the way. I'll get that as close as I can. Okay, now that simplifies and gives us a little more room to work for connecting up the oscillator. So let's go ahead and do that now. This is probably going to be too tight. We'll have to make some adjustments, but you can see it's automatically putting in this chamfer. You don't want to do 90-degree turns or bends in PCB layout. You always want it to have an angle on it. Once again, it's not really critical for low frequency, low power stuff. It becomes more important for high power, high frequency, but it's still just a good practice. And this is an oscillator. It's not exactly high frequency, but it is oscillating. So we definitely want to make sure that we have good notes 90-degree turns. And then this goes up here. I'll just kind of keep these like that. Let me kind of move this. There, that way it's a little more symmetrical. And I may have to move these. Well, this may be too close here. We'll see when we get to the verification process, but don't worry about that now. There's tools that will catch all that and we'll make adjustments. And those are pretty much most of the components. We have Oh, okay, sorry. I did forget. I forgot the load capacitors for the crystal, which are really important. That's C9 and C10. So the C9 goes to this pin. So I'll just put it here. Okay. And once again, this is low frequency, so this isn't as critical as the layout for some higher frequency crystals. Okay, we have those connected. And the only other two passive components are R3 and R1. These are just the pull-up resistors for the I2C lines. These can go anywhere. They're not at all critical. So I'm going to just leave those here. We'll connect up the I2C lines between, which are the communication lines between the microcontroller and the accelerometer, and then we'll place down the pull-up resistors wherever it's convenient to do that. Now we're going to connect up the I2C lines between the microcontroller and the accelerometer. So this is a case where we'll kind of have to route around and drop down, via down to the bottom layer. So this would be a good example of a little bit more complicated routing. So these are our pull-up resistors here. You can see this one goes, this is the I2C SDA line, and that has to connect all the way down to this pin here. I could route through here underneath the microcontroller, and then up would be one way. I could also go around and go through here, but then that's going to box me in a bit to getting the programming lines out. So instead, what I'm going to do is I'm going to route some of it on the bottom layer. Okay, so let's start here. I'm just going to go like this, and then let's go up here. And now I'm going to put a via. So what I'm going to do is I'm going to switch. Since I've got the point tied here, I'm going to, click one more time. So it's tied right here. This is where it's going to put the vias, right where the crosshair is. What I'm going to do now is I can switch to the bottom layer, and it will automatically put a via down. You can do that by selecting up here, but it's kind of, you can see when you do that, then you're dragging this routing line everywhere, and it's showing you all these circles where it's causing shorts and all kinds of problems. So what I just use the hotkey, which is an L, and that's to change the layer. And you can see now we're on the bottom side. So everything you see is kind of faded out, and that's because that's on the other side of the board. Now we're down here on the bottom side. So we just have all the space we want. There's nothing else down here so far. But what we can't do is I can't connect to the chip on the bottom layer because the chip's on the top layer. So we have to just come up here. We'll get kind of near the pin. Click there, and now I'm going to switch and go back to the other layer. And now I'm back on the top. And now I can connect it to the pin. Let me just zoom in here, get that out of the way. There, and you can see now we're on the top layer, so this line here that's on the bottom is ghosted out. And we can just put, this is the pull-up resistor here, so I'll just go ahead and I'm just going to connect it up here for now. We can always deselect, can always move it later if necessary. And now we have that. Okay. Now we have our other I2C line, which is here, which is the clock. And you can see that that's going to go down to here. For now, I'm going to just route this on that layer. We may find that we have to change this as we start routing other things. And we can just, once again, let me just put this here. That is R3, which ties to, that's the pull-up resistor for this other I2C line. And next, the last main thing that we have to connect up is the programming connector. That's the input supply, and let's see where our programming line. Okay, these are the two programming lines here. and they're kind of on the opposite side. We could route them around, but I'm just gonna flip this around. It just makes it a little bit easier. These two lines here, let's just kind of go ahead and move this up. And now we have those, so that should be a fairly easy connection. The issue here that we're going to run into, this is where things get interesting and it sort of becomes a little bit of a puzzle with printed circuit board layout. And that's when, as you get further along, then you start running into less options on how to route. So you have to get a little fancier, either change some of the previous traces or jump to the different layers for routing. So what I'm going to do here is let's jump down to the bottom layer. I'm going to just put this up a little bit. So I'm going to do that. Now I'm going to do L, and then this allows me just to jump over. Forgot I had this guy here. Okay, forget that. I've got this line here, which is blocking me from going on this layer. Once again, I could still go around. The programming lines aren't that critical, but I think what makes more sense is that I move this over to the bottom layer, this line here, and then that way I don't have this boxing me in. So that's what I'm going to do. I'm going to disconnect this, and here we are over here. Now I'm going to switch layers, and now I'm going to go up here and switch back. There. And let me just move this a little bit like that. What this did is it just gave me a little bit of a gap here that I can get my programming lines through. Now we can easily connect up these on the same layer. There. Now we have our programming connector. We still have to connect up the reset pin and the power supply for the programming connector. So the reset pin is going to be pin 10. It's tied to that line. Yeah. Okay. And now we just have this is the input supply for the programming connector. And I think I'm going to just probably short that over here to the capacitors, and then we can just kind of connect everything up together. Okay, I think we have all of the connections. The only thing that we really still haven't connected up is, well, first of all, the power lines. We don't have everything, we don't have all of these connected up. You can see this is the real power line here, and right now it just connects to the accelerometer. All of these others, like this here and this, they're not connected to the supply yet, neither is the microcontroller. So what we'll have to do is we'll have to still have a trace coming from here and tying that into the top. So what we can do here is we can just do a via, and what I'm going to use it for is to connect up. Well, let's move this over closer to the capacitor, to the actual output of the regulator, and we can just tie that to this supply line. Now I'm going to switch to the different layer, and now I'm on the bottom side. Now I'm going to route this power line down here to about here and click again. Now I'm going to switch to the top layer and connect up there. This now connects this one power supply line of the microcontroller got connected up to everything else. We still have this line over here. So I'm going to add another static via. I'm just going to click it there. Actually, let's do about here. Just so the supply goes ideally through the decoupling capacitors before the pin. So I'll just connect up here. And now let me go to the bottom side. And I need to connect this over to here now. Let's just move this one up a bit so it doesn't take up so much space. That's going to create a conflict on the other side. I'll fix that in a moment. We can just move this down here, and now rock like that. And let me move this back. We'll get an error. Now we're going to define the board itself. You have a few options. You can just do place board outline. Now we're going to do copper pores. And a copper pore is basically just a plane. So we're going to be using it for ground planes. Typically you have a ground plane or the positive supply plane. So what we could do is we could make one side a ground plane and another side the output of the regulator, the VDD plane, and then that makes things easier to connect. I'm just going to, because we don't have that much to route, I'm going to just make both sides have a ground copper pore, and then we'll just manually route the positive supply. We can do this because the current's not very high. If we were pulling amps of current through, from the supply, then in that case you would probably want to have a power supply plane, just because you don't have narrow traces. It just will give a much more solid supply voltage to all the pins, because that entire plane is set to that voltage, and then you can just via down and connect into that plane. Okay, so I'm gonna place a copper pore, and I'm gonna go under Objects, Place Copper Pore. Once again, you can draw this, just make 4 points and connect it back, and then we're gonna fix it here. This gives you the specifications for the copper pore, and the copper pore is just going to fill in all the spaces that it can based on these rules. So, like for instance, it's got a clearance of 6 mils is the setting. That's the minimum. That's the closest things can be spaced. So that's right at the edge. So I'm going to give a little leeway, and I'm going to bump this up to 8 mils. It's not really that critical. The main thing is just to set the clearance, and then we're going to go over to connectivity, and we want this to be our ground. So I'm going to connect ground there. And then I'm going to go under border, and this is where it's going to fix the size. So I'm going to just say, make the copper pore depend on the board. I'm going to say snap to the board outline. So it's going to fill in the copper pore automatically up to the edge of the board, and then the clearance, because you can't have metal or copper right up to the very edge of the board. I think I've got the rule set at 10 mils. So once again, just to give you a little space, it's not really that critical. I'm going to just set this to 12 mils, because sometimes you can get an error if you're right at that edge. So just give yourself a little space. And once I hit OK, you're going to see there, it filled in all the space, and this is now ground. Now what we're going to do is the same thing on the bottom. And you can turn on and off the copper pores, because you're going to have to, when you have to make changes, you need to turn off the copper pore, and then have those copper pores all updated. First thing we're going to do is just clear the copper pores, so that allows us to see everything that we need to see. The first thing I want to do is I'm going to add some vias to connect these two ground planes together, because we have a ground plane on the top and the bottom, but they need to be connected together. And for something like this, low power, it's not super critical. You could just connect them with a couple vias, but I'm going to just place a few just vias. Let's just say a couple in the corner, some up here, maybe one near the output of the regulator. And now I'm going to select all these vias and right click on them. I'm going to add to net, because I want to add all these vias to ground, because I'm using them to connect the two ground planes. So I'm going to add to net, and then selected vias, select the net, ground. Okay. Now when I highlight these, you see they turn red, as do everything that's connected to ground. Now I can go back and update the copper pores, and you can see all these vias now they're making contact with this ground plane. Then there's a hole there, and then they come out to the bottom side. Now we're on the bottom, and then they connect to that ground plane as well. You can see these vias aren't connecting to the copper pore. There's a space around them. So this via just connects with this trace here, and doesn't connect in with the ground plane. So that's how you can tell these vias actually connect to that ground plane. Okay, so we've finished the core part of the printed circuit board layout. So the next steps that I'll be getting to in a video I'll share next week is we have to now verify the design and fix any problems found. And there are going to be a few problems that we'll find and we'll have to fix. So I'll go through that in the next video. We'll be checking for both. We need to do a design rules check, which is called DRC. And that's basically, we're just verifying that the printed circuit board matches all the rules that are set by the PCB manufacturer. And this is, the minimum width of a trace, the minimum spacing between traces, all of that. So those are called design rule checks, and we'll do that. And then we also have to check and make sure that the printed circuit board actually matches the schematics diagram. So we'll do that next week. And then after we've verified the design, then the last step is to output the Gerber files and some of the other design files that you'll need to send to the printed circuit board manufacturer for production. Okay, so be sure to watch for that video. I'm John Teal with Predictable Designs, and I hope this has been helpful, and I hope you have a great day. Hey there, this is John Teal, founder of Predictable Designs. If you enjoyed this video and you want to keep learning more about developing, manufacturing, and selling new hardware products, then be sure to subscribe to our YouTube channel and also check out the websites predictabledesigns.com and thehardwareacademy.com.